We will change the track and discuss three IDMT curves as defined by IEC. Normal inverse. This we have already discussed extensively in the previous segment. The two additional curves introduced here are very inverse and extremely inverse. The steepness of curve progressively increases from Ni to Vi to Ei. The generalized IEC equation is shown on the right. By plugging in appropriate values for alpha and beta in the equation, we can find OT1 operating at TMS equals 1 for Ni, Vi and Ei. For Ni, OT1 equals 0.14 by PSM to the power 0.02 minus 1. This is well known to all of you. For Vi, OT1 equals 13.5 by PSM minus 1. For Ei, OT1 equals 80 by PSM square minus 1. For lower current value, say PSM equals 2, operating time of Ei is highest, next is Vi and lowest is Ni. For higher current value, say PSM equals 10, the order gets reversed. Operating time of Ni is highest, next is Vi and lowest is Ei. We will now discuss where to use which curve. Let us start with Vi. Where it is beneficial to use Vi. It is used where substantial reduction in fault current occurs due to large impedance of protected object. It is almost universally employed on HT side of transformer, relay R2 in the figure. For fault on LT side, that is F1, increased operating time for R2 can be easily obtained, to coordinate with downstream relay R1. At the same time, for fault on HT side, that is F2, operating time will be lower, as current seen by relay R2 is very high. Let us compare the performance of Ni and Vi for relay R2 on HT side of transformer. This example was discussed in earlier module. In this case, consider both relays R1 and R2 a normal inverse. For relay R1, curve is Ni, plug setting PS equals 1.2 and TMS equals 0.17. Primary operating current POC equals 3000 CT ratio into 1.2 equals 3600 amps. LT fault level equals 39 kiloohms. Therefore, PSM equals 39 kiloohms by 3600 equals 10.8. For Ni, OT1 equals 0.14 by 10.8, that is PSM to the power 0.02 minus 1 equals 2.87 seconds. Operating time for TMS of 0.17 equals 2.87 into 0.17 equals 0.49 second. This is a straightforward calculation. We have done this many number of times earlier. We will repeat the calculation for relay R2. For relay R2, curve is Ni, same as R1. Plug setting PS equals 1.2 and TMS equals 0.3. POC equals 200 CT ratio into 1.2 equals 240 amps. Reflected fault current equals 2.45 kiloohms. PSM equals 2450 by 240 equals 10.2. For Ni, OT1 equals 0.14 by 10.2 to the power 0.02 minus 1 equals 2.94 seconds. Operating time for TMS of 0.3 equals 2.94 into 0.3 equals 0.88 second. The coordination interval is 0.39 second, a very liberal figure. In this case, let us use VI characteristic for relay R2. Plug setting PS equals 1.2 and TMS equals 0.6. Just in a few moments, you will understand why we set TMS as 0.6. POC equals 200 into 1.2 equals 240 amps. Reflected fault current equals 2.45 kiloohms. PSM equals 2450 by 240 equals 10.2. For VI, OT1 equals 13.5 by 10.2, that is PSM minus 1 equals 1.47 seconds. Operating time for TMS of 0.6 equals 1.47 into 0.6 equals 0.88 second. This is exactly same operating time we got, assuming NI characteristic, for relay R2. For easy visual comparison, calculation with NI for R2 is given. It is just a repeat of what we have done earlier. Now you may wonder what great we have achieved by choosing VI for R2. After all, operating time of R2 is same in both cases. The real advantage comes when we shift the fault to HT side of transformer, as we will see in next. We will compare operating time with normal inverse and very inverse curves for fault on HT side of transformer. For fault F2, fault current seen by relay R2 is much higher and is equal to 15.3 kiloohms. First, we will consider NI characteristics. Relay setting is already fixed in previous slide. PS equals 1.2 and TMS equals 0.3. POC equals 200 into 1.2 equals 240 amps. PSM equals 15.3 kiloohms by 240 equals 64, which is much greater than 20. Hence in IEC equation for PSM, we will substitute only 20. For NI, OT1 equals 0.14 by 20 to the power 0.02 minus 1 equals 2.27 seconds. OT for TMS of 0.3 equals 2.27 into 0.3 equals 0.68 second. Next, we will consider VI characteristics. Relay setting is already fixed in previous slide. PS equals 1.2 and TMS equals 0.6 shown in red. POC equals 200 into 1.2 equals 240 amps. PSM equals 15.3 kiloohms by 240 equals 64, much greater than 20. Hence in IEC equation for PSM, again we will substitute only 20. For VI, OT1 equals 13.5 by 20 minus 1 equals 0.71 second. OT for TMS of 0.6 equals 0.71 into 0.6 equals 0.43 second. This is almost 0.25 second or 250 milliseconds lower than that using NI characteristic. The advantage of using VI characteristic for relay on HT side of transformer is obvious now. We will summarize the results in a single slide. Top left figure is for NI characteristic, and right is for VI characteristic. At bottom left, coordination curves for the relays are plotted. Note that x-axis is in absolute amps. The table at bottom right shows the operating time of relays for different operating conditions. Relay curves R1 and R2 are shown. The vertical line represents fault F1 on LV side of transformer. The operating time is 0.49 second and 0.88 second for R1 and R2 as seen from graph and from the table. Let us consider VI characteristics. See top figure on right. Relay curve R3 with VI characteristic is shown in the graph. Of course, we selected TMS for R3 to make the operating time same as for R2, namely 0.88 second. Now shift the fault to HT side of transformer. 6.6 kV fault line is shown on the right in the graph. The operating time of R2 with NI characteristic is 0.68 second. The operating time of R3 with VI characteristic is 0.43 second. This is 0.25 second less than for R2 with NI characteristic. Let us see now where to apply EI characteristic. Its major application is for backing up fuse. In MCC, outgoing is motor feeder protected by fuse in majority of cases. Incomer to MCC is breaker which gets the trip signal from the relay. What is the characteristic we should choose for the relay? NI, VI or EI? The characteristic of fuse as well as NI, VI and EI are plotted. The fuse characteristic is exceedingly steep, that is at very high currents operating time is very low, say only 10 milliseconds or half a cycle. At low currents, the operating time is very high, in orders of seconds. Consider high resistance fault at motor terminal, which reduces fault current substantially. It is shown as vertical line IF in the graph. In this case, relay with NI characteristics will operate earlier than the fuse, tripping the incomer. The whole MCC is out for an outgoing feeder fault, which is not acceptable. It can be seen that EI characteristics closely follows the fuse characteristics. Throughout the current range, fuse will operate earlier than the relay. We will summarize the observations. EI characteristics is ideal to back up the fuse. For MCC incomer, this is preferred characteristic. Choose VI characteristic for relay on HT side of transformer to backup relay on LT side. Choose NI characteristic in all other locations. When in doubt, try this as the first option.